G'day everyone, how are you going? This video today is on differentiation by first principles. A friend of mine actually asked for this. It was a joke in a little bit of a Facebook chat, and she said, oh, I don't get it. And I said, oh, I'll do a video about it. But actually it comes up in our course just a little bit later on. So doing a video on this now is good. My classes here, they're going to see it a bit ahead of time. So hopefully that helps as well. Hopefully it helps you too. So when we're talking about differentiation by first principles, essentially what we're doing is, how do we work out the gradient of a curve? That's what we're asking. When we've got a straight line, the gradient's no problem. You'd remember this formula here. Gradient is rise over rho, or y values, the difference in them, the x values, the difference in them. That's not so bad, and at a methods level or a year 11 ATAR level, that shouldn't be an issue. But that only works when it's a straight line. So we've got to look for something different in how we work these things. I've drawn y equals x squared, nice easy one to start with. It can be as complex as you like, but let's start simple. If I pick some point, this point right here, it'll have an x value and an f of x value. Because remember, I could rewrite this as f of x equals x squared. Remember, y and f of x, the function of x, kind of interchangeable. Well, they are interchangeable. So x here and f of x here. So that point right there, tucked in there, that point there would be the coordinate x, f of x. Obviously with numbers, but we want to work in the general case. If I come along a value of h, now you can use any letter here, but traditionally we use h for it. Come along h as a distance, I would be at the point x plus h. It's fairly logical. And therefore, that point there would be the value of the function when I put x plus h into it. Okay? So I end up with a couple of points, this one here and this one here. They're the two that we're going to use. Now see this exploded out a little bit here. If I choose an h value a fair way along, I end up with this line here between those 2 points. And you'll notice if I bring h back a little bit, the line changes. If I bring h back a little bit more, the line would change again. Now hopefully you can see that the gradient or the tangent that I would get right at that point is probably about like that. But see, the problem here is if I reduce the h value to 0, that means the first and the second x value are the same, meaning that this would be 0 here and undefined. So I can't actually work out the gradient at a point. And that makes sense because at a point would mean I've only got 1 point. I need 2 points to work out the gradient. So what we do is we say, let's see how far we can shrink this down. See how far we can shrink this down. So we're trying to move h as far as we can this way. All right? So we really want to get it right close here. I can't even draw it. Right close here so that the gradient that we work out is as close as possible to the actual gradient at the point. Yet at the point, the gradient doesn't exist. A little trick. So we've got this. What we do when we're working out gradients for curves is we look at the limit as h approaches 0. Remember, h is this distance that we're coming along here. So as h approaches 0, we want to look at what is the limit, where is it approaching, what is it getting close to. And we use this formula here. Now look at this, f of x plus h, isn't that really just y2? Isn't that just that value minus f of x, that value? Isn't the top line really just working out the distance there? And isn't the bottom line x plus h here, x here, isn't that really just working out that part there? So we're still working out the gradient, but there's a couple of extra steps in here. Let's work through here. So it's equal to the limit as h approaches 0, f of x plus h. Well, remember that f of x is x squared, so the f of x plus h is equal to x plus h squared. So the first thing here is going to be x plus h squared. Just like you'd put 3 into an equation, 5 in, put x plus h in. Minus f of x, well, f of x is just x squared. And remember, that is really working out the difference between that value and that value. And on the bottom line, hopefully you can see that the x's are just going to cancel out. So I'm only going to be left with h on the bottom line. Let's do a bit of expansion here. Let's expand out that bracket. Oops. Now, expanding that out, binomial expansion. It's not x squared plus h squared. It's x squared plus 2xh plus h squared minus the x squared all over h. All right, let's go a little further. Can you see how this minus x squared and this x squared, aren't they going to cancel? They're going to cancel. So do we have now? We have the limit as h approaches 0 of 2xh plus h squared over h. Now, a little trick here is to do a bit of factorisation. We've got h out front of 2x plus h over h. Just factorise the top line, which means that now I can cancel those two. Now, you might say, isn't that going to cause a trouble? Well, no, because I'm working as h approaches 0. I never said h was going to be 0. So h is getting really, really small, so I can do this. But if h was equal to 0, this would be a problem. This would mean I'd be dividing by 0. But I'm not, because it's really close to 0, but not 0. But now what I do, I've got the limit of h as h approaches 0, and what I've got left is, don't need that, is 2x plus h. Now I use this again, because as h approaches 0, doesn't this part become really, really, really small? So the limit as h approaches 0 of this function f of x is actually 2x. I kind of forget about this bit. It's not 0, but it's really, really close to 0. So I say that the limit as h approaches 0 is equal to, well, is 2x. So what does that mean? Well, come right back over here. That means that whatever my x value is, if I double it, that will give me what the gradient is as h approaches 0. Now, it's not the gradient at the point, because remember, I can't work out the gradient at a point because this would be 0. But as best as we can do, the limit as h approaches 0 is equal to 2x. So if I found out later that my x value was 5, that would mean the gradient at that point, as h approaches 0, is equal to 10, 2 times 5. Now this makes sense. Watch this. It makes sense that over here, it would be a positive gradient. What happens when I come over here? The gradient's negative, isn't it? Which would make sense because, say, here at negative 2, the gradient there would approach negative 4. 2 lots of negative 2. And of course that makes sense because it's downhill, isn't it? As I go to greater x values in the negative, the gradient gets even steeper. As I go to greater values in the positive x, the gradient gets even steeper in a positive way. So it kind of makes sense. Now here's a little shortcut. This is good to see, really good to know. The rule is for differentiating polynomial functions, the rule is lower the power, or power out the front, lower the power by 1. So what we can write is actually this. If y equals x to the n, the gradient, which we'll keep it simple for the moment, y dash, there's about 3 different ways to write it, y dash, the gradient, is equal to n x to the n minus 1. I've moved the power out the front, and I've lowered the power by 1. It works, doesn't it? Move the 2 out the front, 2 becomes 1, right here. So what are the big things you need to know about differentiation by first principles? Understand that we're not working out the gradient at a point. That's impossible. We're working out the gradient as it approaches that point as best as we can get. It's very closely linked to our our gradient formula for linear equations. But there's a few tricks on the way through and we end up here. And a bit of a shortcut is to recognise that the rule is power out the front, lower the power by 1, and that'll see you differentiating any polynomial functions. Hope this video helped for you. If you need more videos, check my channel, see what else I've got there. Lots and lots of different videos for you. Catch you later, guys. See ya.